Okay, so we look at multivibrators. Multivibrators. And we start with the bistable. And the name comes from the bi, meaning two. Similar to the one which you did in, or which you worked on the D14 is an unstable multivibrator, which is used as a control circuit. And if you were to do a lot of complex digital programs, then you can break them into a sequence of simple steps, and these steps will depend on the past and on the present circuit conditions. That's why those of you who have done D14, you first did one on the breadboard, and then they gave you a chip which was a flip-flop, the reset set, and then you were supposed to be feeding the outputs from the other circuit into the flip-flop. And I'm sure those of you who have done that experiment and the things came out, you were really happy to see that it looks like the actual traffic lights that I talked about. So, and this is how it looks like. We have a resistor RC here, which is the same value on the other side. And then we have the, I need to coincide with this so that you don't get confused about it. Any problem? So we have transistor T2, we have the Q negation state here, and then I have the RC here. Then it goes to class BCC, RB, T1, and we have Q and Q naught. I'm going to really summarize it, make these more summarized so that we can move on. So this circuit has two possible states. You have when T1 is on while T2 is off, and then you have when T2 is on and T1 is off. So the circuit has two possible states. Stable, two possible stable states. That is when T1 is on, T1 on, and T2 off. The other state is when T2 is on and T1 off. I've interchanged T1 and T2 to make sure that we have the ons here and the offs here. Now, when T1 is on, then we would have VBE approximately about 0.6 volts, VCE approximately about 0.2 volts, and we will say T1 will be saturated. And then we will have VBE approximately being about minus VBB. VBB is down there. VCE2 will be approximately, this is 2, this is 1, 2. VCE1, VCE2 will be the same as, sorry, approximately VCC, implying that our Q would be low and our Q bar would be negation of low, which would be high. Of course, when T2 is on, then the reverse applies. The reverse occurs. In the lab, you had now this being improved and having the capacitor C1 and C2 to store the. So, for example, this one will be basically a combinational logic that you are having this one on, the other one off, but it has to remember whether the other one was off and whether it was on. But if we were to charge, to give a charge along this place here, if we were to have some charge along this other part, so that we have stored charge in the capacitor, as this one is on, it charges, when the other one goes off, then it means we can modify it into a more by including what we covered in the sequential, by including a past state because of the charging that takes place. So that will give us a monostable. If we include this one in the monostable, that is giving it, mono means one. So monostable multivibrator. I'm going to improve this one, whereby I will make these resistances come here and change these ones to capacitors. So I'll remove this and make them capacitors. C1 and have resistance R here. Have the capacitor here. Have resistance R here. And now I will, this is a monostable. So if it is a monostable, it means we have only one of the these other parts being the one which is arranged. So this one, this one will not be, we are only having one stable, monostable, one stable state here. So this one will be, still have the resistance here. We call it R1. This is R, and then we have this R2, and make this one, remove this other one here. And if we do that, we can have the V in here, T1 is okay, T2 is okay. And then it is one step. So we shall have it be out here. Please wait until when I finish the diagram, otherwise you continue rapping like I'm rapping. If you are not using the pencil, you'll be in trouble. I think it is now done. So the other names of monostable, other names of monostable multivibrator are, we can say, a time switch, a monochrome, a univibrator, or a one shot. So Kenya, you can now realize that actually this can help us in timing our switch timing of our TV when you are trying to make it go off after some time. So the circuit has only one stable state. The circuit has only one stable state. Second state is only stable for a limited time, and this time will depend on how long the capacitor can charge. So a limited time determined by the charging RC, and then it goes back. To the stable state. So for this T1 here will only give a state as much as the capacitor can hold the charge. Then it switches back to this other state. For the other bistable, we didn't have this section here, we had a resistor here. So it meant that you can have this state when T1 is on, you have the other state when T2 is on, and this one is off, and they keep alternating in a stable way. But now when you put a capacitor here, if this charge is low, it will swap the other side. It can only maintain its state depending on the values of R and C. And it's unfortunate that most of you have already done D14 when we haven't done this, but at least now you can recollect and be able to visualize. It's not my fault. If we could get a lot of oil, if we had enough of the apparatus, then life would be better. You would all go and do D14 at once, and all of us would be happy. So like for example, tomorrow, all of you will do D14 when we have covered it, and we'll demand another group will do D14 when we have already covered it, and who would have problems? So in V-in is a trigger pulse. This one here is for triggering the pulse or to VCC is for powering our transistors, but this one helps us to have a trigger pulse. V-in is to trigger pulse of short duration, short moment. It makes T1, it makes transistor 1 to conduct, thereby making VC1, thereby making the collector emitter voltage VC1 for transistor 1 jump from VCC to 0. So if we had our pulse, we say the pulse is equivalent to the square wave. If you had a function generator with a square wave, if we took just one part of the because this you have the rising part, then you have the stable where it is stable for a certain specific value, falls back down, goes up. This is our square wave. So if we took one pulse, just one section here, so if we put in V in a pulse, we would get our VCE 1 jumping from VCC to 0. And then we would get it as this, and the output around looking like this. So you can have multiple of them, and then like that. Here it goes like that. So it would multiply. You have this. More of them, but I'm only making one for one pulse. And this would be our TW. The time when it is above 50% of the peak value. And what did we call TW? The pulse width. We do something of the source. We had this, sorry, this one is a bit. And then we had the 90%, the 50%, the 10%, and the time between this other time of rising is what we call the TR. And then this time of falling here from 90%, 10% is what we call as our T fall, falling time or time of fall, when it falls from 90% to 10% of the peak value, and when it rises from 10% to 90% of the peak value, which peak value is here. But then when it is always above the 50%, is when you get it as the T, the pulse width. TW, this time, under which the other state can be stable, that little time, when you can have a stable state, is the same as RC log, natural log of 2, and which is approximately how much? 0.7 RC. You could check in your literature. How many lectures are we left? I'm sure on Wednesday I will not be there. I'll be going for shareholders meeting, so I can't miss. I want to know how my shares are being managed. So I want to apologize that. But Tuesday I'll be here. So Tuesday I'll be able to cover what we are doing today. Bistable, monostable, let's now look at what you did in the lab, which is astable. You can utilize this space here, assuming you are done. So the both states of this multivibrator are stable. So that's why you would, and since they are stable, and then you are having this lighting, this then goes off, and this one lights, and they keep going here and there. So if you were to be here and there, what are you doing? If you keep going this way and this way, what are you doing exactly? You're oscillating. So we also call it, hence it's an oscillator. So it oscillates between two states. And this is how it looks like in your lab manual. So we got the capacitor C1 there, and we have the this is C2, RC, R2. Then we got the transistor here. And then I go the base, across the other side, the other resistor. Then go to the capacitor C1. I'll come a little bit down. And then this one should turn around here. So this is too far. And this one like that. Then we have it to the ground. And I still have to label it as T2. This should be C1. You are late. You are late by 1 minute. So if we can draw the VC1 and VC2, we have the graph like that. On page 260 in the brochure, the graphs for these multivibrator waveforms are clearly shown how to draw it. So I am not worried. Then you have this coming like that, this coming like that. And then if you were to go to the other collector, VC2, then you would have a shift in the graph. So I will have this one here, and now here where it is 0 is when I have it coming up, coming up, coming up. And this is T1. So I have this coming from the other side. So this is T1. And this is T2. T1 we say is determined from the values of R and C. So T1 is equal to R1, C1, natural log of 2, and T2 would be R2, C2 natural log of 2. And the period T would be the same as the sum of the 2 times T1 plus T2, and the frequency of this oscillation will be the same as 1 over T, or 1 over T1 plus. So if you were to be keen on the oscilloscope and you were to look at the time, your time here using the oscilloscope, auto values, and then you compare with the frequency which is being shown on the screen, you would have been able to at least get values in a better way. Next, on Tuesday, we should be able to look at the flip-flops, and which I could have finished today if I hadn't gone into the whatever, but in the first few minutes, we will finish that, and then I give you a hint on the conversion from digital to analog. So basically I can say the lecture on Tuesday will be mostly hinged on digital to analog conversion and the reverse, analog to digital. So you can read about flip-flops and a little bit of the counters, so that Tuesday when I'm wrapping through, you already informed, so that we can actually cover the conversion, because test 3 will cover from where test 2 stops up to where the course ends. The course is here. So today we've been able to cover multivibrators, and next week what is left is the last week or the last part, which is about analog to digital converters, digital to analog converters, analog to digital, the basic features, the full scale range, the resolution of after conversion, what would be the resolution, how to transfer, then the quantization error, and then the method of weighted resistor and flash conversion, which constitutes of the ladder for the dark, and ABC, the flash conversion, successive approximation, and dual slope integrating converters. And I should be able to finish on Tuesday. Wednesday I don't appear. Then Thursday you do the test, and then we see each other on the 27th. Yeah, on Friday. After the test, then we meet on Friday and try to talk about the test and the previous tests, where you have an issue, and also you highlight any issue. If my approach to the course has been a mess, if my attitude has been a mess, you can express your dissatisfaction. I'm intending to put a survey on web, a Google form where you can give your views. It will be anonymous. You can abuse me if you want. I want to know. I want to know who abused me. It will be anonymous. I'll only be able to see it. So when I put that form, express your feelings. Don't worry. Just express your feelings so that you give me a genuine feedback.